So here is an image from the Midwestern United States, which is really well known as a place where there's a lot of agriculture. And one of the reasons that agriculture is so sustainable in the Midwest is because it has really tremendous and rich groundwater resources. So we can all think back to our American history class about a time called the Dust Bowl. And really what brings the Midwest out of the Dust Bowl is reliance on the groundwater in the subsurface. We're going to do a real quick introduction to groundwater and then learn a little bit about how it works and how groundwater played such an important role in Love Canal. So groundwater is found when water occupies pore spaces in soil and in fractures in bedrock. Whoops, I'm going the wrong way. So you can find groundwater in areas like where there are caves, where there's been a lot of dissolution in the subsurface, and you have caves that are connected into caverns and water can flow through there. If you have igneous or metamorphic rocks in the subsurface, a lot of times there'll be fractures and there'll be a lot of weathering along those fractures in the subsurface. Those fractures will become widened as that weathered material is kind of transported away by groundwater, and you'll be able to reliably find groundwater in the fractures of the groundwater system. It's also relatively common in a lot of sedimentary rocks. So these are particles that have been compacted and cemented, but you can see there are still empty spaces or pore spaces that are between these particles. You can see that sometimes there's more pore spaces than others, and that's a concept called porosity that we're going to learn about next. So basically, water will occupy these pore spaces and very slowly flow from one pore space to another. I'm going to show you a video that illustrates porosity and then another really important concept called permeability.
We filled this beaker with about 300 milliliters of relatively unsorted gravel. Notice that there are grains of different sizes that loosely fill the container, leaving several visible open spaces. These spaces represent the porosity of the sediment. Porosity is the proportion of the volume of an earth material that is composed of void spaces.
We can do a brief experiment to determine the proportion of space in the gravel occupied by porosity. We have 200 milliliters of water in this smaller beaker. We dyed the water blue with food coloring to make it easier to see. When we pour the water into the beaker, it fills up the empty pore spaces from below, and the water eventually rises to the top of the gravel.
Now let's look to see how much water we used. Remember that we started with 200 milliliters, and now we have about 80 milliliters left. So we added 120 milliliters of water to a beaker containing what appeared to be approximately 300 milliliters of gravel. That tells us that about 40% of the gravel mixture was composed of air spaces that we subsequently filled with water.
So just to recap, porosity is the amount of a rock or a sediment that is empty space. Now we're going to learn a little bit, but porosity isn't all the story. The rest of it is how connected those pore spaces are, which is an idea called
we
permeability.
have to consider the role that permeability plays in controlling how groundwater moves through rocks and sediment.
Permeability represents the capacity of water to flow through earth materials. It's not sufficient that groundwater is present, it must also be able to flow into our well so that we can extract it.
Many rocks have pretty good porosity, but their permeability values will differ. For example, some igneous rocks contain preserved gas bubbles that are not connected. These rocks would have good porosity, but low permeability.
We've designed an experiment to demonstrate how permeability varies among gravel, sand, and clay, the common sediments at or near Earth's surface. We've taken a funnel and filled it with each type of sediment. We added a tiny piece of filter paper to prevent the sediment flowing through the funnel.
Then we poured a constant amount of water into each setup and watched to see how long it took to collect in the beaker below. The faster the flow of the water, the higher the permeability. Let's see what happened. As you can see, water quickly passes through the gravel and almost all of the original water collects in the beaker below.
In contrast, water pools on top of the clay and is unable to flow downward between the tiny clay particles, making it essentially impermeable at the scale of this experiment.
Finally, water passes through the sand more slowly than the gravel, and only about 75% of the original water makes it to the beaker during the time of the demonstration.
So where this comes into play in Love Canal is the reason why the contamination flowed up and not down, and why the barrels stayed just below the surface. So this is a cross section, which is sort of a vertical slice into the earth in the region around Love Canal. So remember, Love Canal was a canal that was dug into the earth to try to connect the upper and lower Niagara River. So here is that Love, and then it was later filled with hazardous waste and then covered with soil. So here is where Love Canal existed. So when Love Canal was excavated, engineers drilled down through a sandy, silty topsoil, a hard clay, a soft clay, and didn't quite get below to the glacial till or the bedrock below, which was a sedimentary rock called the Lockport Dolomite or the Lockport Dolostone. The other thing that you see here is that this is the average depth of a home basement in the area. So it went through the sandy silt and probably into just the uppermost portion of the hard clay. So here's again our source of contamination. And the other thing you see here are some stars. So this top layer here, the topsoil, is a red star, which means the permeability was about 10 to the 5th centimeters per second, which is pretty slow. But the other thing that's important is that sandy silt has pretty high permeability and pretty high porosity. So a rock layer or a sediment where water can pass through easily because it has a high permeability and a high porosity is called an aquifer. And that's what this uppermost layer was. It was an aquifer. Water could flow through it easily. And the clays that underlaid the topsoil had a much lower permeability. It was 3 to 4 orders of magnitude lower permeability than the topsoil, which means that water passes through it much, much more slowly, if at all. So when water moves very slowly through a rock layer, geologists call it an aquitard. It's an area where water moves slow. So when the barrels were dumped into Love Canal, because the uppermost layer was an aquifer, that toxic waste that leached up and into the topsoil because it really couldn't spread into the clay below. And so that's why the uppermost layer is an aquifer and the bottom ones are an aquitard, and the water, or not the water, but the hazardous waste spread up through the aquifer.